welcome everyone. Before I begin, I would like to formally acknowledge the Ngunnawal people, who are the traditional owners of the land in which I am giving this talk to you today. And I would like to pay my respects to the elders, both past, present, and emerging. And I would also like to acknowledge any Aboriginal and Torres Strait Islander viewers that we have today for this talk. So my name is Nataliea Lowson, and like James said, I am a PhD student studying exoplanet atmospheres at the University of Southern Queensland. And so I thought today I would let you into the world of that research and help you understand a little bit more about it. So before I begin, I wanted to ask the question, or at least also answer the question as to why do we care about exoplanet atmospheres? So I thought I would open the floor to you guys and tell me why you think we care about exoplanet atmospheres.
So it seems like we're getting a whole bunch of questions flooding in now. People think that it's important. People think that the atmospheres could be associated with alien life, it looks like, so that we can know more about the universe just out of curiosity because it's awesome. What do you think about all of this, Nat?
I think that those are amazing questions, and they are quite on the money. So the first reason is we're actually curious. Scientists are naturally curious about the world around us, and we want to know more about it. So that would be the first reason, but also we want to expand our knowledge. If we don't know more about the universe, then we won't be able to have things which you might take for granted today, like laptops, as one big example. But also we want to know about aliens, which I know a lot of you in this talk today are probably here to learn a little bit more about aliens, but we'll get into that a little bit later on. And we also want to know about, or we want to find, the Earth twin. That's like the big aim, I would say, for a lot of planet scientists. And you might ask, what is the Earth twin? Well, the Earth twin is basically a planet which is about the same size as our Earth, would be orbiting a star that's very similar to our sun, and it's pretty much made up of the same stuff to the point where if we went there and set foot on it, we would be able to breathe in the air exactly the same as we would on Earth and be able to survive. I thought I would also start off by actually defining what an atmosphere is, because some of our younger viewers might not quite know what an atmosphere is when I say that word. So in order to understand an atmosphere, you need to understand that everything in the universe is made up of matter, everything that we see. And this matter can come in 4 different forms. There are solids, which is something which is rigid, it has a fixed shape, it has a fixed volume, like a diamond ring. And then there's liquids, which is not rigid. It doesn't have a fixed shape, but it still has a fixed volume, like water in a glass. And then we have gas. And the gas is not rigid, it's not fixed shape, and it's not a fixed volume. We're not going to talk about plasma today, but plasma is the next phase above gas. Gas is important in today's talk because that is actually what an atmosphere is made of. And so as you can see in this picture on the right, an atmosphere isn't just one big gas. It's actually made up of different layers. And in our atmosphere, I think I count 1, 2, 3, 4, 5, 6 different layers. But if we're talking a little bit more scientific, then we like to break up our atmosphere as scientists into 3 different categories, which is clouds, haze, and aerosols. Aerosols being any particles that don't necessarily clump up enough to be a haze or clump up even more to be a cloud. So in terms of scientists, that is how we define an atmosphere around a planet. And you might be wondering, well, what atmospheres have we actually observed beyond Earth? Well, there's actually a lot of atmospheres in our own backyard. In our solar system alone, every planet except for Mercury has an atmosphere. And we even have a moon called Titan, which is the largest moon around Saturn. And it has its own atmosphere. And I've shown these planets and Titan in this image, and you can see that they're all quite different. They don't look the same. And the way that I would like to explain that to you as to why they look different is you can kind of think of each atmosphere being like a cake. So with the Earth, we have, what ingredients would you say you need for a cake? You would need basic ingredients like flour, milk, sugar, eggs. You can also add different things. You can add different color into that mixture. You can add fruits or different flavors. And when you bake that cake, it'll end up looking unique. And you can apply that to each atmosphere in a planet. They're all made up of the same basic stuff, which is gases, but you have different types of gases that mix together, which make these atmospheres unique to their own self. And that's why they look different. So now that you are all experts in what an atmosphere is, I wanted to talk a little bit about how we actually went and observed those atmospheres. So in those pictures that you've seen, we actually took those pictures. And we took them with what is known as a space probe or a satellite, which we launched from Earth and we sent to those planets. And they took the photos for us and sent it back to us so that we could analyze those atmospheres in more detail, so we could learn more about these alien worlds that are right in our backyard. And two of the most famous satellites which we have launched and sent to space is Voyager 1 and Voyager 2. And they were launched in 1977. And to today, in 2020, they have only just reached the edge of our solar system. So they've traveled a very long distance. And because of those, we have been able to find out a lot more about our solar system, be able to categorize our planets into different groups. We now know that there is what is called a habitable zone in our solar system, which is where liquid water can exist. And so much more. But I thought I would just list at the bottom here a few notable missions, aside from Voyager 1 and Voyager 2, that we have sent to other planets in our solar system, and even asteroids as well. And Pluto, I know a lot of you know about Pluto, which is a dwarf planet. We have also sent a probe to look at Pluto too. So, you know all about how we observe them, and you are now professionals in what an atmosphere is. So I thought I would now define the second word in my research, exoplanet. Now, an exoplanet might sound daunting, but it's quite simple. It basically means that it is a planet which is not in our solar system. It is outside our solar system. And we have actually discovered a lot of them. For a very long time in history, it was debated whether planets existed beyond our solar system, but we have found that that is definitely the case. And in this image here, you can see all the planets we have observed up until about 2015. But it's a little bit hard to be able to compare them if we shove them all in an image like this. So scientists use graphs instead. We find graphs a little easier to interpret, and they can give us a little bit more information rather than just staring at an image. And so in these two graphs, it's actually listing all the exoplanets you see in this image on the left and more, because we've discovered more planets since 2015. And we use the graphs, these ones in a sense, I would say, to first understand what they have in common. So on the top graph, you can see that the x-axis, which is horizontal, is measuring how long that planet takes to orbit around its host star in a number of days. And the y-axis, which is the vertical axis, is how big is that planet in terms of how much does it weigh? And so you can see that there is a big clump of green spots, and those spots are telling us that there was a lot of planets discovered by the transit method. And these planets are very big and very close into their star, very different to any planets that we have within our own solar system. And the bottom graph is demonstrating how many planets have been discovered to that date per year. And so as of today, this day, what is today's date? The 13th of June, 2020, we have confirmed that there are 4,164 planets outside of our solar system. I told you that in order to look at the planets' atmospheres in our solar system, we had to send probes. And those probes took photos for us, which had a lot of information in them, and we were able to find out more through that method. However, I also said that Voyager 1 and Voyager 2 are only just at the edge of our solar system, despite being launched about 50 years ago. So I wanted to open the floor again to you guys and ask, how do you think we are able to detect atmospheres of planets well beyond our solar system if we can't actually send a probe?
So lots of people are saying telescopes now. Some people are saying insane telescopes, and then telescopes in all capitals. So there's lots of people think telescopes, reflections, detecting waves. Yes, so the light bending through the atmosphere. So there's some kind of refractive kind of thing that we can detect. Telescopes, ISS, seeing shadows. Seeing shadows, that's not a bad idea at all.
Yeah, ISS being International Space Station.
Yeah.
Well, they're all very good. And you're pretty much on the money. Yes, telescopes is how we observe exoplanet atmospheres. However, you need something to reach those telescopes to see the atmospheres. You can't just have them sitting there and just wait. You need what is called light. And light is all around us. It is why you can see me right now. And we basically wait for light from a star, which a planet is around, to reach our telescopes. And that is how we are able to detect exoplanet atmospheres. And we have come up with 3 different techniques as to how we can do this. The most popular, which I briefly mentioned before, was a transit technique. And that is basically observing a star and waiting for a planet to move in front of the star. And when the planet does that, it actually dims the light ever so slightly so that we can see that there is a difference in light coming from that star. And because we can see the star before the planet is in front of it, we know how much it shines on its own regularly. So when the planet goes in front of it, we can simply subtract the light from the star, and it will reveal the light coming from the planet. In other words, it will reveal the atmosphere of the light coming from the planet. So that is the transit method. The second method is called direct imaging. And direct imaging is similar to transits, but rather than waiting for a planet to go in front of its star, we use what is known as a coronagraph to actually block the light from the star. And when we do that, we can sometimes see planets beyond that light. And so the top image I have here is an image where they have removed the star from it, and you can actually see 3 planets. And of course, from that, the light coming from those planets will also include light from its atmosphere. And the last method, which is slightly more difficult to understand, is called Doppler imaging. And what that basically means is when you have a planet orbiting a star, they will actually be causing, how would I put it? They'll be making each other wobble because the gravitational interaction between the 2 of them will be doing this. And that wobble will cause the light to actually shift a little bit, which you can see in this bottom right image, that the light is shifting from the red to the blue. However, the planet's interaction on the star won't be very big because the planet is very small. So the star will only wobble a little bit. However, if we remove the star again from the data, like we have done with the previous two methods, the star's interaction with the planet will cause the planet to wobble a lot. And so you'll be able to easily pick up the light coming from the planet and therefore its atmosphere. So these are the three confirmed methods we can use to actually detect atmospheres from other planets using telescopes. But what does it look like when we actually do this? Well, I mentioned before that you can see me because of light. In particular, visible light, because the human eye is able to detect what we call visible light, which is a region in the entire electromagnetic spectrum, which is basically a fancy word for all the light that we know of. However, there is more light beyond what we can see with our eyes. And we know this because we have detected it over the years of being curious and wanting to know more about the world around us. And so, like with most things that you look at in the universe, if you look at it in a different region of light, it'll unlock a different area of that object for us to discover. And so what you can see in this image is when we look at an atmosphere through different regions of light, we can actually find out different information about it. For example, if we were to look at it in optical, or the light that you and I can see with our eyes, there is different gases that we're able to detect than if we were to look at it in the infrared light, which goes further into the atmosphere, which in this image shows different gases. And I also thought to bring it a bit closer to home, I would show you what this looks like for Jupiter. And so for Jupiter, the further you can see that there are different clouds, and the further down we go, those clouds are made of different gases. And we can also see with this straight line that does that curve, the temperature gradient of Jupiter. And that the further into the atmosphere that you go, the hotter it becomes. So there's lots of information we can actually determine just by looking at the light in different regions. So now that we've done this, what have we actually found? Well, in our solar system, or what we perceive to be the normal in the universe, we have three different types of planets. We have rocky planets, which is like the Earth and Mars. They form slowly and they remain small. And most importantly, if we're talking atmospheres, the atmospheres are very thin compared to the planet itself. Then we have gas giants, which is your Jupiters and your Saturns, where they form very fast and they're very big and their atmosphere is very thick compared to the actual body of the planet. And then we also have ice giants, which use Uranus and Neptune. And they also form slowly like the rocky planets, but they formed further out. And they're not necessarily called ice giants because there's a lot of ice in their atmosphere. It's just a fancy word that we use to try and distinguish it from the gas. But the main difference between ice giants and gas giants is that gas giants will contain a gas called metallic hydrogen, which you don't find in ice giants. But what did we find once we looked outside our solar system? Well, we found planets we didn't even think were possible to exist. One of the most famous ones being a hot Jupiter, where it is a planet that is the size of Jupiter, but it is in an orbit so close to its star. You could basically say it's orbiting where Mercury orbits in our solar system. And so the atmosphere of that planet would have to be made of completely different gases than what the atmosphere of Jupiter is in our solar system in order to survive such a close, hot region. But that's not all. We also have super Earths, which are rocky planets, but they're a lot bigger than any rocky planets in our solar system, which is why we call them super. Now that's the same with super Neptunes, and hot Neptunes are very similar to a hot Jupiter, but they are planets that are around the size of Uranus and Neptune. And we also have rogue planets, which are planets that don't even orbit a star. So those worlds would be very dark and very interesting to explore. But in this image, you can also see that we have a detection gap, which is basically a region of planets that we haven't been able to discover because our telescopes are not powerful enough yet to discover those planets. And we're talking planets that are around the size of Earth, which is why when you hear stories in the media about planets that have been discovered and they sound exciting and they're very close to Earth, but they're never Earth-sized, or they're rarely Earth-sized. And that is because we don't have the telescope power yet to find those planets, but they're definitely out there. But I know what most of you came for today, and that is aliens. What about the aliens? We have all these planets. Surely one of them has aliens on them. And that's probably true. But can we detect aliens using atmospheres? And the answer is yes, we can. However, I need to step back and actually redefine what we define life to be. Because you might define life to be like you and I, walking, talking animal, which flies in a spaceship and then comes down to Earth and rules over all of us forever. Not necessarily. So life can be anything that's alive, whether that be an animal like us, or a tree, or bacteria, which is life that is all around us right now, but we can't see it unless we have a microscope. So that is first what scientists would define as life. We're giving ourselves a very easy basis to go off first before we start going, let's find life like a human. And we can actually narrow down where we can look for this life. And one of those regions is called what is known as the habitable zone. And I briefly mentioned it earlier when I was talking about how we have sent satellites in our solar system to explore our neighboring planets. Well, the habitable zone, just to remind you, is a region around a star where a planet will orbit where it is not too hot or too cold for liquid water to survive. And you might be wondering, why is liquid water so important? Well, it's important to us because we know that most life here on Earth relies on liquid water to survive. And so if the only successful life we have found so far, being life on Earth, needs liquid water, then it's highly probable that other life beyond our solar system will need that too. So that is that's one way we can narrow down the search. Another way is what is called the red edge signal, which is a signal that we have been able to find when we have actually looked back at our own planet to see if we can use our own telescope's current technology to detect life on Earth. And when we did this, we basically saw that in the region between 700 and 750 nanometers, which is the very red edge of visible light, there was this huge spike in emission. And we figured out that this is actually coming from plants on Earth, because plants use the sun to, you could say, eat. The way that they survive is they actually absorb sunlight. But they don't absorb all the sunlight, they actually reflect some. And one region of light that they really reflect, don't want it at all, is this red edge signal. So that could be a way, if we look at an atmosphere and see that huge spike in that specific region, that we could detect that there are plants on the surface of a planet. But there is a third way. And the third way is called the magic biosignatures, which is 4 agreed upon gases that have been associated with the life cycle on Earth. However, we have to be careful if we do find these in other atmospheres, because there are other processes that can produce these gases. It's not just life on Earth that can produce them, and nothing else. So if we were to find these on other planets, there would have to be more than one of these gases. It can't just be one and then we go, oh, there's an alien there. So these are the 3 main ways that we can use exoplanet atmospheres to detect potential life on another planet. So what have we learned so far? Well, exoplanet atmospheres can be used to understand the chemical features of our atmosphere, which is the gases, looking at the gases to understand what is actually there. But we can also use it to understand the physical features of our atmosphere using such as temperature or weather or pressure. They're all very important too. It can also help us to understand how a planet formed, because looking at these atmospheres, it's actually a way that we have used to try and understand how planets are formed in our own solar system. And I can go into more detail if anyone asks me about that later. But we can also use it to detect alien life. So before I go, I thought I would share some resources with you that are available if you are interested in looking more into planets. So for example, there's an exoplanet coloring book that NASA has released. So if you like coloring like me, you can go through that book, color in planets, and it will also tell you fun facts about the different types of planets we have found. But there is also the Exoplanet Catalog archive, which is on NASA too, where you can actually click on every single planet out of those 4,000 that we have discovered, and you can see what type of star system it's in, the physical features that we have been able to confirm about it, and even some of the chemical features, depending if that atmosphere has been probed. And finally, there's also a fun little app that you can download on your phone called Exoplanet Excursions VR, which basically you can take photos and then you can change the background in your image to make it look like you're on one of these alien worlds. So thank you so much for listening to my talk, and I hope that you learned a lot about exoplanet atmospheres.
Awesome. Thanks so much, Nat. I think we
Right.
all learnt a lot just then about exoplanets and their atmospheres. Very, very interesting. And I really like the analogy that you had with cake, saying that different cakes are made out of different kinds of things, and every planet is like its own special little cake. That was very cool.